So this class has a private instance variable. It's probably the only time you'll see me declare a private instance variable, but I want to do this to give you practice of manipulating state through methods that have side effects in this class. So when you have objects of this type, of type number protector, how do we modify that state when we don't have direct access to it? Now, the Scala community, for the most part, says let's just let everybody have access, but just for this to be able to modify state through reference is the big thing I want to get some practice with. I'm going to have a private variable. So number is not able to be accessed, but this class does have two methods, both of which have side effects, meaning that calling the method changes the state of that object. So we can either reduce the number, which decreases that value by 3, or we can access the number, which is going to return it to us, but not before it increments it by 1. So every time we even check what that number is, it's going to change that state. So this is a very dynamic object. That state is going to change no matter what method we're calling. So we have to be careful about what we're doing. And the lecture question is to write a method that takes in an object of type number protector, and no matter what number is, actually that's not necessarily true, but no matter what number is, call these methods such that number is equal to 0, that underscore number. That's not strictly true now that I think about it. I forgot to add it to the lecture question, but I won't test it with negative inputs. Though negative inputs, you should be able to handle those as well. I'm not testing them, but I guess technically you can handle them anyway, the way it's written. So how do we just call these two methods to manipulate that state to be the value that we want it to be? Okay, interpretation versus compilation. These are two very different paradigms that programming languages adhere to. So with interpretation, when you write a program, your code is going to be executed one line at a time. It's going to start at the top of your program, at the very first line of your program, or the very first line of your main method, and just execute line after line until the program's over or it crashes. Compilation, on the other hand, when you write your code, all of that code is compiled or translated into a completely different language. And then that code that it was translated into is then interpreted by an interpreter. That code is ran line by line. But the code you type in a compiled language is never actually ran line by line. We think of it that way often. We think of it as running line by line, but it's actually being compiled into a different language, and that language is being ran line by line. So we'll see some differences with these two types of languages, and especially as you go throughout your career, you'll see the differences between these two types of languages. So first, interpretation. 115 is all about interpreted languages. Python and JavaScript, interpreted languages. Strictly speaking, Python is kind of compiled, but not really. Effectively, it's an interpreted language, same with JavaScript. So here's two programs written in Python. And when you have an interpreted language, the interpreter is executing your program line by line, which implies that it's never looking ahead. It's never checking your code aside from the line that's being executed. So with this, you get a lot of runtime errors. If you have errors at all, they're often going to be runtime errors. With JavaScript and Python in 1.15, your code would run, it would hum along fine, and then hit a line of code that had an error, and then crash. So for example, this code on the left, and I'm throwing in an example of classes. I think I linked to it, but I didn't mention it in lecture. So I want to give you an example of a Python class. For this, the constructor has to be specified separately with this specially named init method. And the first argument of every method is always explicitly self, which is the same as this in JavaScript, which is a reference to the calling object. So Python makes it very explicit that these are methods through that parameter of self, where usually that's implied in most other languages, including Scala. It's implied that we have a reference to this being called with that method. So here I'm creating an instance of this simple object. So I'm creating an object of type, or of this class. I'm creating an object of type runtime error example. It's getting an initial state equal to 5. I'm going to call add to state. It's going to print this line, add 10 to 5. I'm going to print out the state, and it's going to print out 15. Nothing too interesting. Your first example of classes in Python, but other than that, we're adding 5 and 15 and printing it to the screen, just through some extra stuff that we're doing on top of that. Now, similar to that, let's look at the program on the right, which is the same, except when I go to add 10, I got someone being smart and giving the string ten instead of the integer value 10. Now, when this program is run, we're going to create our object just the same. We're going to call add to state. It's going to print adding to state. This program will print adding to state. It gets to that line, it runs that line, and everything is fine. When it gets to this line, when this line is interpreted right here, and it tries to add the string ten to the int 5, this is where the runtime error occurs and the program crashes. So the program ran up to this point, so we did get some execution of this program, but once we got to that line, program crashes. This can be a bit dangerous and a bit painful to debug at times, because you can have an error like this in a method that can be called like this, and maybe you have some code possibly inside a conditional that has an error like this, and then during your testing, if you don't have thorough unit testing in your Python code, you might never hit that conditional, that condition that has the error, which means in your testing, your program runs fine. But then once a user gives an input that triggers that conditional and runs the broken code, their software crashes. They report a bug, they're mad at you, you have buggy code, you have a buggy program, you have buggy software. Even though all your testing is fine, but if you don't run that line, or if you don't do comprehensive testing, you might miss these runtime errors. It happens fairly often. I've had my fair share, that's for sure, where you're chasing down a runtime error, trying to figure out what's going on, and it's just because it's an input that you didn't test that does break your code. Compare that to compiled languages. This includes Scala, Java, C, and C++. So a lot of the languages you'll see moving forward, I'm sure you'll all still mess around with Python and JavaScript. You'll still see those languages. But once you start writing larger programs, well, we tend to like the advantages of a compiled language. So these languages are all compiled. And now instead of seeing runtime errors, we're more often to see compilation errors. So what this means is when we write our code, and the compiler is converting our code into code in a different language, while that's happening, the compiler itself is checking for errors. So that error that we saw on the previous slide, which is duplicated here in Scala code, this error right here, the compiler will find that and will not even translate your program. It doesn't know how to translate this program. It won't translate your program into the other language. Your code will never be able to run. You cannot run even a single line of code in this program. Nothing will run at all. So this can be frustrating because you can't run any part of your program, but it's often very helpful because if you do have a bug like this, the compiler gets in your way and says, whoa, 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 whoa. Let's fix this before we move forward because this is going to cause a lot of issues down the road. And it does prevent a lot of those issues. It stops you from moving forward with code that has a bug in it because it'll stop you right at compilation time. It'll say, no, let's not move forward. Let's get this fixed because when I do get to that line of code, it's going to break anyway. Let's fix it now. So it's just helpful. So this code on the left, this compiles, runs just fine. This code on the right, once it gets to this line, it's going to say, expecting int, got a string, fix this, because I'm not running it. Not even going to try. An issue that we're almost guaranteed to see, it's a very frustrating one. I want to warn you about it now, is when you're working on lecture questions or even homeworks, if you have a lot of code in your project, a lot of you like to have one project with all your lecture questions, which is great, that's fine. If you have an error in any file anywhere in that project, your code won't run. The compiler won't build the project, it's not going to run your code. So the bug has almost no symptoms because you're looking at your lecture code, you're 100% sure, you're positive that your lecture question code is completely correct. The TAs are going to look at it, I'm going to look at it, we're all going to say, your code is 100% great, that should be getting full credit. But when you have an error somewhere else in your project in a different package that you were just messing around with, but lecture started, so you had to jump over to lecture and jump away from that code, but you left it with a compilation error, that's going to cause some issues. It's not an issue if you're testing your code, if you're running unit tests, if you're running your main, you're going to find that compilation error real quick. But not all students do that, and then we got those kinds of errors. So one of my first things usually is run your code, show me your tests. It'll get rid of a lot of those issues. So that a compilation error can be anywhere in the project, and none of the code in that project will run, because the compiler won't compile it. Some more advantages, I consider compilation errors an advantage. Yeah, they can be annoying. For example, JavaScript, you can have errors all over your code, and JavaScript will just try its best to run it. It's kind of hard to get a JavaScript program to crash, and often you get acceptable behavior from pretty buggy code. Compilation errors are a bit more strict. I see that as an advantage because it's going to end up you're going to end up producing higher quality code. In addition to that, the compiler is kind of fixing a lot of your code, and maybe fixing is the wrong word, which is why I put it in quotes here, but the compiler is going to add a lot of efficiency to your code. So as it's doing this translation, it's going to look for a lot of places where your code isn't quite as optimized as it could be, and it's going to fix that to be able to be better code, more optimized code. For example, if you have a variable, you declare something a variable, but you're never going to change it, I believe the compiler is going to change that to a val and store it differently, treat it differently in memory, so it can be more efficient. For example, here's one thing that Scala's compiler is going to fix for us. And we'll talk a bit more about this in the last example today, but this code here should cause a stack overflow. It's going to fill up your entire stack memory with stack frames and just blow up. It's going to completely break. That actually doesn't happen in this case. Scala looks at this, sees that it's something called tail recursion, fixes that, makes it so it's not tail recursion. It turns this recursive function into a recursive method into an iterative method. And then this code, of course it's still broken, but it'll just run forever without causing the stack overflow. That's one thing that the compiler is looking for, finds, fixes, and in this case the code's still broken, but we don't crash. We just spin up our CPU, burn up our fans and everything, burn up our hardware. Scala specifically, I keep saying that compilers translate your code into code in a different language. The code that Scala is compiled to is called Java bytecode, which is the same language that Java is compiled down to. Compiled down to Java bytecode, so a compiled Scala program looks just like a compiled Java program. And in fact, they can be mixed. We can have Scala and Java code in the same programs. And we've even already saw that. We have ScalaFX and JavaFX running in the same program in the jumper code base. We have these languages being mixed because they both compile to Java bytecode. And that Java bytecode is ran on the JVM, which is installed on literally billions of devices around the world. If you've ever seen these notifications that says, update your Java, that's your Java runtime environment, or your JVM, your Java virtual machine, which interprets Java bytecode. This is different from your JDK, your Java development kit, which is made for writing code that will run on the JVM, on the JRE. So if you've ever seen these pop-up messages, that means this machine can run Java bytecode, which is the vast majority of devices out there. You probably never had to install, well, you have to install Java, but you never really had to think about it. Oh, I want to run this game, I want to run Minecraft written in Java. I better download Java first. No, it's already going to be on your machine. It's already installed. As opposed, one other side note, languages like C and C++, these languages are compiled right down to what we call machine code, which is the code that your processor itself is able to run. So when people, if you've ever heard C++, C, they're more efficient, it's because they're being compiled directly down to the lowest level code possible. It's all just ones and zeros, it's all machine readable code. The Java bytecode has to be interpreted again as it's being ran on the fly into bytecode. So there is one more step to go from Java bytecode to actual machine code. But those are topics for another day, not 116. Topics for 116. We still want to talk about the heap and the stack. I want to show some more examples and reinforce what's going on the stack and the heap in memory and how it affects us. And specifically, references. The big thing I want to get across in 116, references. Objects are passed by reference, which we'll talk about it even more when we get to Monday's lecture. So let's look at some code and trace through the execution of a program that puts multiple objects on the heap, and just trace through this and see everything that happens while we execute this program. With stack and heap, I believe the best way to see this is to visualize it through examples. So I'm going to go through a couple of examples today, reinforce what's going on with the stack, what's going on with the heap. So without further ado, let's just jump into this one. So we have a main method in two classes. The very first thing our main method is going to do is create a new instance of one of our classes called bird. Bird has two state variables. I want these always to be initialized to 0 no matter what. So I'm not putting them in the constructor. I'm not allowing the calling code to be able to modify the initial state of objects of this type. I always want them to be 0, so I'm not putting them in a constructor. I just have an empty constructor. My constructor doesn't take any parameters, no arguments. But I am creating two state variables, one that can change and one that cannot, and one method. So when I say new bird, I'm saying operating system, the JVM is going to talk to the operating system and say, we need memory, we need enough space to be able to store 2 integers. Operating system is going to find you enough space somewhere in memory. We don't know where, we don't care where. But somewhere in memory, in the heap space, we're going to get enough space to store this bird. The new keyword, this call, is going to return the memory location of where we can find that bird. So we're going to return this index just somewhere in memory, whatever memory locations the operating system gave us. And I should start throwing hex in these. These indexes usually have hex. They're hex values. Technically, I guess I still have hex. I just don't have any letters in there. Anyway, we return this. We're going to store it in a new variable of type bird, a value of type bird, named bird, and store only that memory address. Which the details get a little murky. Technically, in the JVM, it's not directly memory address, but it's instructions on how we can find that memory where this new bird is stored. And we can think of it as a memory address. Next, we're going to create a variable named action. It's of type string, and assign it the value nothing. This effectively will go on the stack. There's a lot of little nuance points in this. I don't want to get too bogged down in details. Technically, strings go on the heap, but they're something called immutable, so they behave like they're on the stack. So we're going to pretend this is on the stack even though it's on the heap, but whenever we pass a string into a method or a function, it's going to effectively make a copy of that string and not pass just the reference. It will technically pass the reference, but it just behaves different. Strings are very complicated in the JVM since they are immutable. I don't want to go down that rabbit hole, so we're going to pretend that it's on the stack because that's how it behaves. Now we're going to call a method. We're going to call bird.inDanger. That means we're creating a new stack frame on the stack, calling this method, going to times checked. It's the only times checked that exists in our program, but if there were more times checked variables, we would look at the innermost scope. We're inside this block. Well, first we're inside this block. We're going to look for something called times checked. doesn't exist. We didn't declare it locally in this method. So we're going to look at the next block. The object, the calling object, does have a times checked variable, so we're going to use that variable. I usually like to make this explicit and put this dot times checked there to get rid of any ambiguity, but just to show scoping, I don't want to put the this there. It's going to look for the most inner scope of where it can find a variable with that name. If I had a parameter named times checked, the way I have this code written, it would find that parameter, increase the parameter by 1, and not touch the state variable, which would not be the behavior we want in this case. So we're going to run this line. That means we're looking at bird, following this value, going to this place in memory, finding times checked, and incrementing that value by 1. So we change that, even though this method returns a Boolean, it doesn't return an int or anything, it still changed a variable in memory. So that value's changed, we return true, so we're always returning true no matter what. We're just calling this method for the side effects mostly. Since that's true, we're going to go into the if statement. We're inside the if block. The stack frame for the method call is gone. The method call is over, so that frame's gone, but we're inside the if block now. We're going to create a new value named action of type string with value panic. Now things get a little more interesting. So we created two variables, well, one variable, one value, both named action. So now we have to be careful about which action is going to be used at different parts of our program. Right now we're inside of this if block. So if right now we use a variable named action, we're going to see the variable named action that's storing the value panic. As soon as we exit that block of code, we're done with that if statement, that scope, that block is over. We destroy any variables that were declared inside of that block. So that variable named action storing panic is now gone. And when we print action, we're printing the string nothing to the screen. So that one word, that one keyword val right here, gave us some behavior that we probably don't want. We probably, if we have code like this, we probably meant to modify the value of action that was already declared as a variable. We probably didn't want to create that string, assign it a value, and then just throw it away right away. We probably didn't want that. So we got some behavior that we didn't quite want because we weren't careful with our scoping. Next, we want to create an instance of our other class, our box class. This is going to take two references of birds as inputs and just have one method that's going to call a method on those birds. So this box, I'm going to create a new box. I'm going to say, hey, JVM, tell the operating system I need some memory. That memory needs to be enough to store 2 memory addresses to be able to locate these birds. I'm going to give it one bird that we've already created. So I'm going to pass this reference to that constructor. And I'm also going to create a new bird in line. This is what we call an anonymous object. This is an object that we create, but we never assign it to a variable. So we have no way of referencing it directly. We have no way of referencing this bird. So we created a new bird that also went on the heap with its own values of times helpful and times checked. And then in the box's constructor, we have bird1 and bird2 with those memory addresses of those 2 birds. So there's quite a bit going on in that line. Are there any questions up to this point? Okay. So in this main method, we have no direct access to this bird. We can only access it through the box. Box is the only place where we have a reference to that second bird that we created. We're going to hit our next if statement, so we have to resolve this Boolean expression first. Boolean expression is called the box.endanger. Box.endanger calls bird1.endanger and bird2.endanger. So I'm putting two new stack frames on the stack. I'm not creating new variables, so I'm not too concerned with how these stack frames are working, but there are two stack frames put on the stack. I'm going to increment times checked in bird1. I'm going to call bird2.endanger and increment its times checked as well. So I can modify that bird, but I have to do it through box, because box is a reference to that second bird. The second bird can then be accessed through the box. That's the only way I can really access it. And you'll notice, good as time as any to mention this, both of my references in main I'm declaring as val, but the values that I'm storing are kind of changing. So when I created this bird, the value in bird has changed twice since I've created it, but I've declared it with val, so bird can never, ever, ever change. That's what val means. So how do I get away with that? Well, this is an implication of the references. The value that bird is storing is only the memory address. It's only a reference. And that reference never changed. The value stored in bird never changed. But once I followed that value, once I used that value as a reference, went to that location in memory, I went into memory and started making changes. So when you declare an object variable as val, the reference cannot change, but that doesn't mean that the object itself, the state of the object itself, can't change. The state of the object can certainly still change, even though it's stored in a val and not a var. But I could never do something like bird, like down here maybe. I couldn't say bird equals new bird. I can't replace that reference ever. It's always going to refer to the same reference, which is often what we want. So it's nice to have these as vals, so you can't replace the reference and have it refer to an entirely different bird later on down the road. It's usually not what we want to do in our code. Okay, so box.endanger, it was true or true. Another nuance point. Technically speaking, I don't want to get into this nuance of a point on an assignment, so I have it in the slide in a way I can just talk about it. But technically speaking, when bird.endanger returned true, this is an or statement. So if I have true or anything, it doesn't matter what this value is. This is always going to be true. The or statement is always going to be true. When that's the case, Scala doesn't evaluate the other side of the or statement. It's going to shortcut the evaluation to save some time, and it's never going to call bird2.endanger. So technically, bird2 times checked would still be 1 in this case. I should probably update the slides to make that more explicit, just in case somebody is tripped up on that. But the general rule of thumb is if you have Boolean expressions like this, don't call methods with side effects, because you might get strange behavior in these cases. But bird2.endanger technically wouldn't be called here. So for anyone who's watching that who knows about that stuff, yeah, I know. I just wanted to focus on the stack and the heap. Maybe I should update it though, but I don't know if we need to get into those details. All right, so this was true. I'm going to enter this if block. I'm going to modify the existing action. So now I'm doing the thing that we should have done in the if statement earlier, where we shouldn't be declaring new variables of type of called action. I'm going to use the action that exists. I don't have one in scope already, so I'm going to find this one. I don't have one in the if block, so I'm going to find this action. And set it equal to this value, stay in the boat. Now when I print out action at the end of this if block, now when I print it out, I am printing in stay in the boat. I'm not printing out that string nothing anymore. I did actually change the value in main. In the variable of type in the variable named action in the main scope, in the scope of the main method. Then we hit the end of our program, give all that memory back to the OS, and get on with our letters. So quite a bit going on. This code is in the CC116 examples repo. I highly encourage you, and I'll show an example if I have time at the end, which I don't think I will, but I strongly encourage you to open this code, run the debugger, and step through that code one line at a time to watch everything that's happening. You should see the same exact stuff here, with the exception of bird2.inDanger won't be called. You should see the same execution, the same stuff happening, the same frames on the stack, the same instances in heap space. You should see all that in the debugger. So any questions on this example? Covered a decent amount of ground. I guess not new ground, but new applications, more complex applications of what we saw on Monday. Any questions about this? So we saw multiple objects on the heap in heap space. Let's talk about multiple stack frames on the stack. We're going to look at this recursive algorithm that's going to compute the geometric sum. So given a number, I want to compute the sum of every value from every integer from 1 to that number. So input of 3, I expect to be printing out 6 here. So I'm going to call this recursive method. A recursive method is a method that calls itself. So as long as my input is positive, I'm going to compute the geometric sum of 1 less than the input, add my value to it, and then return that result. So if compute geometric sum is correct, I can call compute geometric sum of 2 and add 3 to it, and that 2 should be returning 3, plus 3 I should be getting my 6. If I have compute geometric sum of 2, I should be calling geometric sum of 1, which should be returning 1. I'm going to add 2 to it to get my 3. Calling it on 1, I'm going to add 0 to it, return 1. And when it's 0, I'm just going to directly return 0. That's the behavior I'd like. I have it set up. It should be doing that. But let's look at the stack and see how that's running in memory to see what's going on here to be able to get that behavior. And after this example, we will table recursion for a bit. We will see it in, I think, 4 weeks. Recursion will make a big return. I just want to give you a taste of it now to get you, get that idea out there of what recursion is. So recursion's a slippery topic. It takes a bit to fully grasp. If you're not fully comfortable with recursion right after this example, do not panic. That's fine. That's normal. That said, I think you should be able to follow the example, especially when I show all the stack frames. But when it comes to writing your own recursive methods, that gets a bit trickier. So don't panic if you can't do that yet. You shouldn't be there yet. If you are there, awesome. If you're not, don't panic. So, same thing when we start our program. Our command line arguments go on the stack, which we don't have any. We're not using those. And we're going to put our first method call on the stack. We're calling compute geometric sum of 3. Starting a new stack frame, creating a variable named n for the parameter, assigning it the value 3 from the argument, and then running this method. When we're in the method, n greater than 3, or 3 greater than 0 is true. So we're going to go into this if statement. We're going to start an if block. The very first thing we need to compute is compute geometric sum of 2. So we're going to create another stack frame. We're going to call this method with a value of 2, set its parameter named n to 2 in a new stack frame, and we'll call this method again. Same thing, 2 is greater than 0. We entered an if block. We put a new stack frame on the stack. We assigned the parameter equal to the argument, which is 1 in this case. And we call that method again. So you start to see the pattern here. And we'll eventually get down to where n equals 0. So at this point, we have a lot of variables on the stack, all named n, all of type int. So when we're inside one of these method calls, it's important that we're using the correct value of n, which is handled through the stack frames. So right here, when n equals 0, oh, I need one more click. When n equals 0 and this is false, and we return 0, we know that our value of n, well, we're not using the value of n, but the value of n is the value of n that's inside this stack frame. Once we return 0, we're at what we call our base case of the recursion, and we can start returning values back up the recursion. So we're returning 0, we're destroying this stack frame, and returning the value 0 from that frame. So now we're back in this stack frame that we had. We're back to looking at this value of n, which equals 1. And now we have our first return value of 0, and we're storing that in a variable named result. So now we're inside a stack frame that has an n, it has a result, and we have all these other values of n up here that are still in existence, but they're not currently accessible until we return from the current stack frame. So now we're going to run through our code. We'll add n to result. We added 1 plus 0, nothing interesting. And then we're going to return result. This is the last line of our code. There's nothing after this if statement. So we're returning result, which is 1, and destroying that stack frame. Now when we destroy that stack frame, we're going back to the previous stack frame, and we're going back to the line of code where we created that stack frame. So when we created that previous stack frame, we were resolving this method call. So we're going to go back to this line with that value. We'll replace this with the value of 1, assign it to this new variable named result, and move on with our code. We have this value of n. The value of n in this stack frame is 2. So we're going to add our 2 plus 1 and return 3 from this stack frame. We return that. That destroys this whole stack frame. In this frame, we were still resolving this method call, so we'll go back to this line. In this stack frame is going to get that result of 3 by evaluating this expression, this method call expression. That returns 3, store it in result, add result in n. n in this stack frame is 3. Add that to the 3 in result. Result is 6. Return that. Destroy that stack frame, which brings us back to main, the main stack frame, which was waiting on the very first call of geometric sum. That returns 6. Store that in a variable named result, and just print it to the screen. All that computation, we're not doing anything interesting. But that's how our recursive method would happen when we have multiple stack frames on the stack. That's how that's going to be resolved. So we had a lot of variables on the stack, all named, a lot of them named n, but we were always be able to keep track of which n we should use at which point. And again, I encourage you to go through the debugger and see how that execution works. And certainly with your homework, of course, due tomorrow, go through the debugger on your code, see how your code itself is working, make sure you have things going on the way you expect. Yeah. I'd have to look at that example. We can chat. Then we hit the end of our program and we free up memory. All that memory is back to the OS. So in that previous example, we got close to the end of the stack. What would happen if we went a little bit further and we started interfering with another program's memory? So we get rid of this if statement, change our code a little bit, call the same method, but we don't have the if statement. So this is what this is going to do is enter what's called an infinite recursion. It's just going to keep calling itself and keep adding stacks to the frame indefinitely. So when we got to this point, where at this point we would hit our base case and start returning back up the calls. This time we're going to keep going. We're going to keep adding values to the stack with negative inputs and just keep going and going and going and going. What's going to happen is we're going to fill up all of the stack space that was available to us, that the operating system gave us. We're going to start trying to use memory used by another program, and we're going to get the infamous stack overflow error. We overflowed the stack, we used up more memory than we were allowed to use, program crashes. So using up your stack space, always going to be a bad time. And we're back to the lecture question.